External respiration takes place in the lungs. It is the process in which exchange of gases takes place between the alveolus and the pulmonary capillary. Air that's inhaled arrives at the alveolus, crosses the alveolar wall, crosses the capillary wall, and ends up in the pulmonary capillary. This way, oxygen diffuses from the alveolus to the capillary. Carbon dioxide diffuses from the capillary to the alveolus. There are 5 factors that affect simple diffusion, and they also affect external respiration. Membrane thickness, when it increases, decreases the speed of diffusion. Membrane surface area, when that increases, it also increases the speed of diffusion. The third factor is pressure gradient. When the pressure gradient is high, the speed of diffusion increases. The partial pressure of a gas increases the speed of diffusion. The greater the partial pressure of a gas, the greater the speed of diffusion. The solubility of the gas in water is also important. So the greater the solubility of the gas in water, the faster the speed of diffusion. These last 2 factors, partial pressure and solubility, come under Henry's law, which we will talk about a little bit later. Membrane thickness is the one factor that when it increases, it actually decreases the speed of diffusion. This makes sense because when you have a thick membrane, this would present a greater barrier for substances to diffuse. So the greater the membrane thickness, the slower the speed of diffusion. This becomes important in pneumonia. When a person has pneumonia, the amount of fluid that accumulates in the alveolus is so high that it actually makes the alveolar wall much thicker than normal. As a result, the diffusion of oxygen and carbon dioxide is extremely slow. So that's the alveolar wall, and here is the mucus that accumulates on the inside of the alveolar wall. This lowers the speed of diffusion, and the speed of diffusion is so slow that it can no longer support life. So that's why people with pneumonia die. In the lungs, the membrane surface area really comes from the alveolar walls. If the alveolar walls are intact, then the membrane surface area is high and the speed of diffusion is also high. So the greater the membrane surface area, the faster the speed of diffusion. This is for the normal lungs. In patients with emphysema, this becomes a problem because the alveolar walls are destroyed by cigarette smoke. So the membrane surface area is decreased greatly in emphysema patients, and so the speed of diffusion also goes down drastically. As a result, oxygen cannot diffuse fast enough into the tissues, and there is chronic hypoxemia. So let's take a look at the alveolus that's normal. And this is the alveolar sac being damaged. The walls are damaged. In emphysema, there are no walls in between, and this greatly reduces the speed of diffusion. The next factor we take a look at is pressure gradient. The greater the pressure gradient, the faster the speed of diffusion. In this graph, we will look at 3 different situations of the partial pressure of oxygen with a different gradient. The yellow line represents a very steep gradient. We are in a hyperbaric oxygen chamber. Here, the pressure of oxygen is at 2,500 millimeters of mercury, which is very high indeed. So, when a patient is placed in a hyperbaric chamber, the gradient is so steep that oxygen quickly diffuses into the tissues, promoting healing. The next situation is normal. represented by the green line. The green line shows that the ambient partial pressure of oxygen is 158 millimeters of mercury. This is the normal gradient. Oxygen diffuses into the tissues at a normal rate, thereby supporting life. The third situation is represented by the white line and is at high altitude. At high altitudes, the ambient partial pressure of oxygen is only 110 millimeters of mercury. In this situation, the gradient is reduced and therefore the diffusion of oxygen is also slowed down. So when the gradient is steep, the diffusion of oxygen is very fast. At a normal gradient, the pace of oxygen diffusion is normal, and at a reduced gradient, the pace of oxygen diffusion is slowed down. So here's a recap. The greater the pressure gradient, the faster the speed of diffusion. According to Henry's law, the diffusion of a gas depends upon its partial pressure and the solubility of gas in water. So, the greater the partial pressure of a gas, the faster the speed of diffusion. Now, when we think about inspired air, nitrogen has the greatest partial pressure. The amount of nitrogen in atmospheric air is 78%. Oxygen is only 21%. By this account, nitrogen should be the one that crosses the alveolar wall, crosses the capillary wall, and ends up in our bloodstream and in all of our tissues. However, that is not the case because nitrogen is not soluble in water under normal conditions. It is oxygen that satisfies both rules. Oxygen has a fairly decent partial pressure, about 21%, and it is also soluble in water, and so it is oxygen that ends up in our tissues. So let's make this clear. Under Henry's law, we now know that in normal conditions, it is oxygen that ends up in our tissues. So oxygen diffuses across the capillary and alveolar walls, and they end up in all of our tissues. Nitrogen, on the other hand, does not diffuse across the alveolar and capillary walls because they're not soluble. It is not soluble in water, and so it ends up being exhaled along with carbon dioxide. The solubility of nitrogen can change profoundly in the ocean depths. Let's see how that happens. At sea level, atmospheric pressure is considered to be 1 atmosphere. At 33 feet below sea level, the atmospheric pressure doubles. At 66 feet, it triples. At 99 feet, the atmospheric pressure is 4 times that of the atmospheric pressure at sea level. At this high pressure, the solubility of nitrogen changes profoundly. Nitrogen, which has a very high partial pressure normally, increases even more at this very high pressure. And so it overrides the solubility factor, and nitrogen can diffuse across the respiratory membrane and reach the body tissues. This happens when a scuba diver reaches the depths of 99 feet. Nitrogen can enter the tissues. So nitrogen now enters all the body tissues, including the brain. When it reaches the brain, it causes a narcotic effect called nitrogen narcosis. This is a pleasurable state which is often referred to as raptures of the deep. Once the scuba diver wants to come up again, they must do so very slowly. This is important because this allows time for the nitrogen to slowly leave the tissues as the pressure keeps decreasing. As the pressure decreases, the solubility of nitrogen also decreases, so it comes out of the body slowly. However, should the diver come up too quickly, then there is not enough time for all the nitrogen to leave the body tissues. Nitrogen now becomes sequestered in the brain and in the joints. This causes a painful condition called the bends or decompression sickness, because the nitrogen that is bubbling out of the joints causes great pain and discomfort. Deep sea divers are advised not to fly for 24 hours since their last diving incident. This is because the 24-hour period will allow enough time for all the nitrogen to leave the body via exhalation. If the 24-hour rule is not followed, then there is a higher risk for a diver to experience acute decompression sickness. This is because when the airplane takes off, it gains altitude and loses pressure rapidly, and this can bring on an acute decompression sickness, because any nitrogen that's trapped in the body will come out rapidly and cause great pain in the joints and produce other symptoms of decompression sickness.